In this session, I'd like to introduce the important quantity in physics, angular momentums. When we consider the one-dimensional motions, so we could consider the momentums, p equal mv. Momentum is a vector quantity because the velocity is a vector quantity. When we consider the rotational motion of an object around some axis, so in this case, the object with a mass of m is making a circular motions with a radius of r with a velocity of v. Then we could consider angular momentum is a vector quantity is defined r cross p. P is a momentums. If you write that p is mv, angular momentum is expressed r cross mv vector quantity. So direction of the angular momentum is perpendicular to the circular orbit of an object. This is the definition of angular momentums. The angular momentum and the torque is closely related. So when you consider the derivative of the angular momentums, so you can substitute L equal R cross mv. Then we can use the derivative of the product of the two functions. R cross v is this is derivative of R cross mv plus R cross derivative of v with respect to t. Then b cross b, this becomes 0 because the vector quantity of the same vector becomes 0. And the m dv dt is equal to the f. So you can move to the next line, r cross f. This is the definition of the torque. So we discovered rate of the change of the angular momentum of a particle equal to the torque of the net force acting on it. So dl over dt equals the tau. This is a very similar equation motion of the Newtons. This is dp equals df. This is a very similar equation. When you consider the rotational motions instead of the equation motions, you should consider dl over dt equals tau. So L, angular momentums, plays a similar role. With momentums. Then conservations of the angular momentum. When there is no force acting on the systems, total momentum is conserved. If the total torque acting on the system is 0, we could derive the conservation of angular momentums because dl dt equals torque. So in this case, the torque is 0. Then L becomes a constant values. When the next external torque acting on the system is 0, total angular momentum of the system should be conserved. Then finally, I'd like to explain the angular momentum of a rigid body object. So we consider rotational motion of the rigid bodies. Again, we'd like to divide a rigid body object in the very small pieces. So this is the standard method we use when we consider rigid body object. Then sum up small parts. So if you consider small parts of the rigid body object, this blue part is making circular motions around the axis of rotations, and the angular velocity is omega. Then velocities is expressed v sub I is equal to r sub I times omega. And the angular momentums can be calculated r sub I times m sub I r sub I. This is the velocity. This corresponds to the p sub I momentums. Then r sub I momentum is a perpendicular. So this is r sub I, and p sub I is perpendicular. So sine theta becomes 1. Then this becomes expressed m sub I, r sub I squared times omega. Omega is the same quantities for all the parts of the rigid body object. Then to find out the angular momentum of the rigid body, you just sum up all the parts. So take a sigma in the both sides. Then this part exactly equals the moment of inertia. So angular momentum of a rigid body is expressed I times omega. This is the angular momentum of a rigid body. This is the end of this session.